everyone, welcome back to another awesome episode of Virtual MOSI. My name's Jose and this is Light Week. So throughout the week, we're actually going to be talking about light, we're going to be talking about how the human eye sees, and all sorts of really neat facts and activities that you can try at home that deal with light. Today we're going to be focusing more on what light is and how it fits into the electromagnetic spectrum. So kind of on this wall behind me here is a visual representation of what the electromagnetic spectrum comprises. So what is the electromagnetic spectrum? Well, it's really a propagation, a changing in fields that deal with wavelengths. Now, all of these different types of what we would call radiation actually are perceived stars or galaxies and things like that. It's just that typically those stars will radiate this type of energy in different forms. So let's break that down a little bit. Let's ignore my shadow on the wall here, and let's end of the spectrum. This is actually the section that has the shortest wavelengths, meaning it has the highest frequency. And I'll explain a little bit what that means momentarily, but these are essentially going to be your gamma. So earlier when we were talking about Nebula, when we were talking about the time you have a very rapidly oscillating pulsar, you are emitting these really fast moving, very high energy rays of radiation. And then, of course, we can bring that down a little bit. We tone it down. And if you go to the doctor, maybe you fell and hurt your arm and you need to get some x-rays done. X-rays are not nearly as energetic as, say, gamma rays. You're not going to turn into the Hulk from getting an x-ray. And you'll find that they are a little bit lower on the radio spectrum here. Now, if we move on past X-ray, we eventually run into ultraviolet rays. And UV rays, we know it as UV light, that's actually called ultraviolet because the frequency is just past the violet end of the spectrum of what we call visible light. So it's just past, it's just higher than violet, so we call it ultraviolet. And the opposite end from UV, we have infrared. So our prefix infra means beneath or lower than red. And so the infrared light would actually be just beneath the red end of the visible light spectrum. And notice this is a very large diagram. And here you have kind of an expanded version of the visible light spectrum. In reality, the visible light, the light that you and I can perceive with our eyes, only makes up a tiny sliver of this whole spectrum. That means that whenever we see red light or blue light, even green light, it's actually a specific range of frequencies that the human eye actually reacts to. We cannot physically see ultraviolet light or even infrared light, and we definitely can't see radio waves or microwaves or things like that. So our human vision is limited to just a tiny, tiny sliver of the whole spectrum. Now I'm going to leave this up on the wall for just a moment. I'm actually going to change that visual, so bear with me. You should still be able to hear me for as long as I continue talking. That visual now is going to actually show us kind of some typical things that we might know that actually utilize that certain level of the spectrum. So, of course, as the name implies, radio waves, they all actually transmit and broadcast using radio signals. Now, believe it or not, when you're sending a spacecraft to space, obviously, and you're trying to send signals to it, you utilize radio waves. Now, radio waves are not sound waves, just like light is not a sound wave. These waves are actually very special. All of these types of waves are special because they don't require a medium to travel. That means that the sounds that you hear now are because I am moving the particles in the air here. If I were underwater and tried to make sound, it would work, not the same as here in air, but if I tried to speak in a vacuum, or if I were to clap my hands in a vacuum, since there's no medium for the waves to propagate, then unfortunately there would be no sound transmitted. These waves don't require a medium, so these waves can all move freely through space. That's why we can see the light from faraway stars and even the sun. That's why we can feel the warmth of the sun in ultraviolet and infrared radiation. And that's why we can study faraway galaxies using X-ray telescopes, using radio telescopes, and all sorts of different tools that let us see more than just the tiny sliver of the electromagnetic spectrum. So, of course, radio waves utilize the longer waves, and if you look on this particular diagram, they also have the waves kind of drawn out. This is what we would call a very long wavelength, because the distance between the wave peaks is much farther apart. So it is a much longer wavelength. And if you were to take a chunk of this and keep it constant throughout your spectrum, you'd notice that if I take about a foot-long chunk here, I only have about half an oscillation in radio waves. And yet if I move on to something much more energetic, say like gamma rays, then suddenly I have like 5 oscillations. However many fit in that little chunk, that's what we would consider the frequency. Now, this is not fully to scale, because radio waves can actually be about 1 kilometer long. That's right, one of these little crests can be just about 1 kilometer away from the one behind it. And next time you tune in to the radio, if you're listening to 103.9, that's actually in gigahertz. Megahertz. So 103.9 megahertz is about 139 million hertz, or doing this frequency. So that's pretty cool. Now, if we move on to microwaves, as the name implies, microwave ovens actually use the microwave portion of the spectrum to heat up and cook your food, which is pretty neat. And something that you might not notice is that the remote controls utilize the IR, or infrared radiation. You can actually test this out if you have a remote control at home. You can click it towards the direction of your cell phone's camera, and you might actually see a little blinking light. Unfortunately, we can't see that light, but your camera, digital cameras, are far more sensitive. I actually have with me a full spectrum modified camera, and this camera can see wavelengths that the human eye can't normally see. I actually, if I want to use it in the daytime, I have to put on a special filter in the front that would block the ultraviolet and infrared light, because otherwise my pictures would get a bit of a weird color to them. And if we try using this in an outdoor environment, all of the colors would be different. Things that would normally not be blown out would be blown out in the image, just because the sensor in the camera is far more sensitive than our human eye is to all these other levels of radiation.
Mr. Jose,
yes?
I was wondering, can his cat see more types of light than he can?
Ah, that is a great question. There are actually several animals in the animal kingdom that have much better vision than humans. Actually, the animal with the best vision is the mantis shrimp. It's not really a mantis nor a shrimp, but its eyes can detect a whole lot more of this electromagnetic spectrum than we can. Cats, they typically have better low light vision, meaning that their eyes can gather more light. It's almost like having big binoculars. When it is darker, you're able to gather more light. I wouldn't necessarily say that they're able to see ultraviolet or infrared radiation. But I know that certain insects, particularly bees, they actually do use UV and IR detectors in their eye structures in order to actually find flowers that they can then help pollinate. So, great question. And then we, of course, we're all used to actual light bulbs. Turns out some light bulbs back in the old day would also emit a lot of infrared radiation. Part of the reason why, if you have ever tried to get close to an incandescent light bulb, it starts to feel really warm. That's because the infrared radiation over time, it does actually are associated with it. And then as you move on, you'll go on to X-rays and gamma rays, and that's what we consider radiations. But remember, light is also radiation. It just doesn't really hurt. Now I'm going to move on for a second. I'm going to share another image up here, and this is going to actually show you how different parts of the spectrum can be very, very cool to observe. Also, how they can help us better visualize different phenomena. And Miss Janet, if we could hit some of the lights, just some. Fantastic. This should hopefully help bring the image a little bit, make it sharper on your screens. Now, as you can see, we are observing the sun. Now, most of the sun that you might see will probably look kind of like this. And that's kind of a broad spectrum. That's kind of what the eye would see if we could safely observe the sun. We also are kind of used to seeing images like this. This is actually limiting all of that radiation that the sun puts out to a very, very particular narrow band. In this case, it's about 304 Armstrong. This corresponds to just about the hydrogen alpha emission line. Essentially, that means that the sun is putting out a whole bunch of radiation in this particular frequency. Now, there are all of these different types that we can observe, and notice how there's different detail that we can garner from the different types of images. So, for example, we can see the sunspots in visible light, but we couldn't really see all of the energy and the difference in the magnetic field that the sun had unless we utilized all of those different filters. So that's kind of neat. And moving on from the sun, our closest star, we can actually observe the remains of long-gone stars. And this, what you're observing here, is actually the Crab Nebula. Now, the Crab is a supernova remnant found in the constellation Taurus, the Bull. And if you were to observe it through a telescope that's large enough, you'd actually see a fuzzy cloud that kind of looks like this. Now, the human eye can't really make out a whole bunch of color when that light that hits it is very faint. So that fuzzy cloud is going to look just dull gray in color. But if you have access to an awesome telescope and a good camera that can take longer exposures, then you can actually start to get some of the coloration in the image. And then if we study the same object with radio waves, we're no longer observing light with that same frequency. We're actually observing light that is being emitted by that supernova remnant, and it has a different range of frequencies. So, for example, with the radio waves, we can observe kind of the electrons interacting with the magnetic field. And then here in the ultraviolet rays, we can see kind of the section of that supernova remnant that has energy level. Finally, with X-rays, it's even difficult to see what you originally started with. So the X-ray image doesn't really look like the optical image anymore. And what you're looking at is a remnant of the star that once lived there. So it's definitely pretty cool, definitely pretty neat. Now let's go ahead and show you guys on my little whiteboard here kind of a hopefully smoother understanding of the difference between wavelengths and frequencies. So clearly, we have a line that's drawn with orange marker, and then a line that's drawn with blue marker. Now, I mentioned earlier that red light, that actually has a much longer wavelength. Once again, if we count the spacing here, if we look at the spacing between the peaks of the crests, you'll notice that the spacing is much farther apart. That means that it has a longer wavelength and lower frequency. So red light doesn't actually have a very high frequency. And it's for that very reason that anytime you're doing astronomy, all the space stuff is because I'm one of the resident astronomers here at MOSI, you typically want to use a red flashlight or a red headlamp. This, when it gets dark, you can actually still see around you. You can still read the charts of the night sky, but the red light is not going to damage your night vision as much. Otherwise, you would have to wait about 15 minutes for your eyes to adjust back to the darkness. So red light has a much longer wavelength, much lower frequency. If you look at something like blue light, you'll notice there's far many more tiny peaks in that same space. That means that the frequency is actually a whole lot higher. So the frequency is higher, and the wavelength, the spacing between those peaks, is a whole lot shorter. So much higher frequency, shorter wavelength, blue and violet lights, they'll have a much higher effect on your eye. And to better visualize that, let's go ahead and take a look and see what happens if we turn off the lights here. So if we manage to turn off the lights, it should get very dark. But if I use my astronomy laser, you might actually start to see a thin green line that's hopefully going to be picked up by the cell phone. If not, then when we are able to once again host Skywatch events at the museum, our astronomers actually utilize these types of lasers when it is nighttime to actually point out stars and constellations in the sky. You just need to make sure there's no aircraft around and be careful not to aim the beam near or around a person or animal. That would be not very fun because, again, green light, very, very high wavelengths. Now, our eyes actually react a whole lot more to green light than, say, to red light. And that's simply because the way that our eye is based. Now, I know we're going to cover the eye more in a little bit throughout the week. So we're actually going to observe this other laser that I have. You'll notice it's a slightly different color. It actually does not have a very visible beam, and that's because our eyes react a whole lot more to green light. I'm going to go ahead and use this time here to take a look if there's any questions, and we can go ahead and bring the lights back on.
We have a couple questions.
Yeah.
We'd like to know, can laser light be invisible to the human eye?
Yes. So can laser light be invisible to the human eye? The answer is yes. You typically don't often see the laser beam, even if your eye is very dark adjusted. And that's working with small pointers. If you're working with large industrial scale lasers, then you actually can see the beam, and even if you don't see it, it can hurt your eyes if it's shown directly into your eyeball. So yes, certain types of light radiation, if it's shown directly into your eye, can actually be painful, even if you don't see it. So that's why oftentimes you'll wear those. With pointers, it's not much of a problem. With larger lasers, that definitely would be the case. And another one.
And Leah has heard plant lamps to give her indoor plants light, red and blue. If she could only buy one, which is more important? Or could she just use a purple one?
Ah, that is a beautiful, beautiful question. Which light is best for plant growth? There's actually been several experiments done where you try different types of growth lamps and see what works best. Turns out that when you look at a plant and you look at their leaves, the color that you see is actually the one color that the plant is not absorbing. It's the color that it's reflecting. So when leaves appear green, all of the reds, it's using up all of the blues, all of the purples, and it's not using the green part of the spectrum at all. So I would recommend the red lamp. The red lamp, or even the purple one, grow a little bit better than if you just tried a green one. And I have a couple of filters here. Perhaps this might be a good time to kind of share what. Very bright green dot on the wall here. If I use a green filter, then absolutely nothing will happen on the laser. And that's because the green filter is actually not altering any of the other lights. On the contrary, if I use a red filter, then you should see that the green dot on the wall grows considerably shorter. Okay? So if you have lamps that emit light in only the green portion of the spectrum, then the plant might not actually use that too well. So I recommend the red plants for sure. All right, guys. And if there are no more further questions, I'm going to go ahead and do a super quick recap, and we'll call it a day. So, frequency. Frequency is essentially the closeness of the peaks. Okay, how many of them there are? The wavelength is the closeness or the distance between the peaks. So a much longer wavelength will have a shorter. Sorry, go ahead.
It's a question.
Yes, I love questions.
Catherine asked, does frequency and wavelength relate to music at all?
Ah, yes. So frequency and wavelength definitely do relate to music. Music, again, is using sound waves, which is different from light and the rest of the electromagnetic spectrum. But you are correct, say, a flute. If you cover up all of the holes that you can on a flute, you're effectively making the body of that flute longer, which means that the wavelength that can form inside that tube, longer wavelength, and in turn that's going to have a lower frequency. So the more holes you plug, the lower the note. And then as you open up more holes, then you're essentially shortening the length of the instrument, or the body that can, the wavelength that can form inside the instrument. And so the shorter it is, the much shorter wavelength you can form, the much higher the frequency, so the note or the pitch will be higher. Now, amplitude is something that we haven't really looked at, and essentially amplitude is the volume or the intensity of the wave. So if I have a wave here that matches the wavelength of my original orange line, but you'll see the peaks are much, much higher. The amplitude, or the distance between the middle point and the peak, that amplitude is actually going to give us a much higher sound, meaning louder sound, because it will have more energy associated with it. All right, so we've got frequency, we've covered light as part of the electromagnetic spectrum. Now, please do be sure to stay tuned throughout the week. We're going to be doing all sorts of fun experiments on light and how the human eye sees light. And then we'll end the week with some really cool tricks that your eyes can play on you using light. So thank you guys so much for joining us in this other episode of Virtual MOSI. Once again, my name's Jose, and keep discovering.